So what I'm going to try to do in this video is make a series of calculations during a titration of a weak acid. So the acid is weak and the base is going to be strong. So what I want to do is I'm going to set this up. Standard graph would look like this, pH there, milliliters of base added down here. What I would expect to get out of a titration of a weak acid with strong base is a curve that looks something like that. Alright? Well, during this calculation, I'm going to try to calculate the pH at the equivalence point, the initial pH before any base has been added, a halfway pH, or the pH at a halfway through the titration, and then another one, maybe about 35 milliliters up. So numerically, I'm going to try to derive those. Now the first calculation that I'll do will be the initial pH. So let's say I have, I'm starting off with 50 milliliters of acetic acid, HC2H3O2. And what I'm going to do, it's 1 molar in concentration. I'm going to add 1 molar NaOH in these amounts. The first amount is I won't add any. So the first would be 0 milliliters. Okay. Then I'm going to go to 25 milliliters. Then I'm going to go to 35 milliliters. And I'm going to go to 50 milliliters. Alright, so those are going to pick up the green points that I have on the graph above. So I'm first going to start off with what the pH of the 1 molar acetic acid would be with no base acid. So what's going on there, acetic acid, HC2H3O2, is going to break up into hydrogen ion plus the acetate anion. Looks like that. Now initially, might as well do an ice chart for this one since I can. Looking at an ice chart, give you practice in that, the initial concentration of the acetic acid was 1 molar. I didn't have any of this or that because they haven't ionized yet. There's going to be a change of X amounts of the hydrogen ion and the acetate ion. And remember, those are always going to be in the same amount because they're coming from the same molecule. And that means that the change in the concentration of the acetic acid would be a minus X. Now at equilibrium, I'm going to ignore these X's because this X is too small to make a difference in my original concentration. So my equilibrium concentration for the acetic acid is 1 molar. This hydrogen ion concentration becomes X, as does the salt. The mass action expression says that H plus times C2H3O2 minus molarity divided by the original molarity of the acetic acid on the bottom will all equal 1.8 times 10 to the minus 5, which is the Ka for acetic acid. Now that value has to be given to you in order to do these calculations, but it probably would be given to you, alright, or you'd have to go look it up. So substituting into this one, I'm going to have X times X over 1 molar equaling 1.8 times 10 to the minus 5. Solving for X, X then is going to be equal to 0.0042 molar. So that means the hydrogen ion concentration is equal to 0.0042 molar. And now all I do is take the negative log of the hydrogen ion concentration to find the pH. So that means it's the negative log of 0.0042. And when I do that, I'm going to end up with a pH equal to 2.37. And that seems pretty reasonable because it's a weak acid and so forth. Alright, so that's when no base has been added. Alright? Now, this next one, I'm going to add 25 milliliters of NaOH. Now, if you remember what I had in there in the first place, I had 50 milliliters of the acid. And the acid concentration was 1 molar. Well, the base's concentration was 1 molar. So this, in essence, is halfway between the equivalence point, the end when I have equal number of moles of acid as base. And that's always what's going to be the case in a titration. So I'm halfway to H plus equaling OH minus. Alright? And something happens then, because what's going on when you're halfway is half of the acid have been neutralized, leaving behind the anion. And so the concentration of the anion is equal to the original acid that you started out with. And it's kind of hard to sort of visualize, but here, this is what's going on. You have HC2, H3O2, and it's going to H plus C2, H3O2 minus. Okay, and I'm sitting there adding base into it. Now, as I add base to it, the base is going to neutralize the acid, and the result is going to be H2O. I just neutralized that amount. Now, Le Chatelet's principle says, as I decrease the concentration of the hydrogen ion, the equilibrium is going to shift in a direction to replenish that loss, meaning the amount of the acetic acid in the first place is going to go down, leaving behind an acetate ion every time one breaks apart. So one of these breaks apart, breaks into one of these, which gets neutralized to water, leaving behind an acetate ion. So you're going to reach a point where the concentration of the acid right here is going to equal the concentration of the salt right there. And so what I can do in terms of finding what the pH is going to be at that point is saying, okay, and I'm going to use kind of the same buffer calculation. I have the hydrogen ion concentration then is going to equal the Ka times the concentration of the acid. Oops, I messed that up. The acid over the salt. And it just so happens that those are equal. So now hydrogen ion concentration, H plus, is equal to the Ka, which is 1.8 times 10 to the negative fifth. Going through the whole rigmarole, I'm going to find out that the pH ultimately is equal to 4.74. So think about that. But remember, this is, the acid is being broken up because of the removal of the hydrogen ion. So as this quantity starts to get smaller, the amount of salt that's in there starts to get bigger. Okay? And there's going to be a point where this is getting bigger, this is getting smaller, that they equal each other. At that point, which is always halfway between the equivalence point and the original, means that the pH is real simple to calculate. Alright, so there's that. Well, that's that one. Now a little bit trickier. Now what I'm going to do is I'm going to add 35 milliliters of the 1 molar NaOH to the 50 milliliters of the 1 molar acetic acid, HC2H3O2. Now the only way that you can go about doing this and standing a good chance at it is realizing that I got to work in moles because my final volumes are going to be different, because these are going to add up these are going to add up to a new volume of 85 milliliters. So my concentration when I go to find the pH is going to be dependent upon that. So the first thing I want to do is I'm going to find moles of OH added. Alright? And it happened to be that I had a 1 molar solution, and I'm going to multiply that by 0.035 milliliters, mLs, and that's going to mean that I'm going to be adding I have added 0.05 moles of base. Going to find the moles of the acid that are sitting in there. I'm going to mess that up. It's not that OH, it's H+. Okay? So I had 1 molar acid. I had 50 milliliters, or 0.05 liters. Okay, and I put milliliters in there, but I meant, make that nicer. Maybe I can, if I scrunch everybody together there, I can maybe write it all out. So I had 1 molar NaOH. I had 35 milliliters, which is 0.035 liters, and that gave me 0.035 moles of base. Didn't really make that much difference. Whereas this one is going to give me 0.05 moles of acid. Okay? So, I'll do a nice chart again on this one. What the heck? So here it is. I'm back to my HC2H3O2. I tend to sometimes keep going back to this because it sort of gives me a foundation on what to base my C2H3O2 base my calculations. Okay? And let's put in a nice chart again. ICE, what the heck? So I'm going to go like this. Well, the initial concentration right here was 0.05. So I had 0.05 of that stuff thrown in there, and I got that from this calculation right there. Okay. Normally, with these, as these calculations go through, I have X of that and I have X of that. All right. Then what I ended up doing was I ended up adding 0.03 moles of base. Well, what that's going to do is that is going to decrease the hydrogen ion through neutralization. We don't really know what it's going to do to it because it's X, but I do know it's going to increase the amount of salt by 0.035 moles. Because every time I take away one of these, I'm upping one of these that I get out of it. Which also means the amount of the original acid is going to decrease by that 0.035 moles. And for some reason I left off the 5 over there, so we'll go back and pick that up. Put the 5 there. Which means at equilibrium, okay, I'm going to have 0.015 moles of the acid. I'm going to have X of the hydrogen ion concentration, and I'm going to have 0.035 moles of the base sitting in there. Now, we got a new volume, so I'll go and I'll check and mess around with that. The new volume, okay, the new volume I already said was 0.085 liters because that came from, that 0.05 liters came from the addition of the 35 milliliters of base to the 50 milliliters of acid that was already in there. So to do these calculations, okay, the calculation for my new concentration of H, I screwed that up, so let's go back. HC2 H3O2, okay, from my calculations on the other page were 0.015 moles, now divided by the 0.085 new volume, giving me, alright, 0.176 molar of the acid. The salt, the H3O2 minus the anion half was 0.035 moles. Divide that by this new volume of 0.085 liters, given me a concentration of 0.412 molar. So now, back to a mass action expression. It's going to be the hydrogen ion. I should maybe write that so you see it. So again, well, it's the same darn thing. It's H plus times the C2H3O2 minus over HC2H3O2 concentration. That whole amount is going to equal the Ka, which means it'll be X times 0.412 divided by 0.176 equaling 1.8, same Ka, 10 to the minus 5. Make a long story short out of this, X is going to be equal to 7.69 times 10 to the minus 6. I go through all my contortions and I end up with the pH being equal to 5.11. Alright? I finally got there. So that's a little bit more involved. Alright? Now, we're going to go to the equivalence point installment on this whole thing. Now, what happens at the equivalence point is all the acid has been disassociated. So here I go. I'm going to add 50 milliliters of 1 molar NaOH to 50 milliliters of 1 molar HC2H3O2. Okay? Now, going back, I might as well put a, the reaction in here. I have HC2H3O2 going to H plus plus C2H3O2 minus. I'm sitting there adding base. The base is neutralizing the H2O, the hydrogen ion into H2O. The reaction the equilibrium has is more and more of the acid is going to break up. Well, eventually, what's going to happen is, if I went through and solved this, I'd find that I have the moles of, because it is the equivalence point, the moles of the H plus are going to equal the moles of the OH minus. And that's what happens at the equivalence point. Alright? So that means all of this is going to be gone. And it also means that the concentration that originally I started of the acetic acid, which is 1 molar, alright, is now going to be not the concentration, because I got to get the moles out of it, but the number of moles. So I'll mess that up just a little bit. Not a big deal, but it's not the moles of that, or the concentration. So the moles of the acid now are going to be equal to the moles of the salt that came out of it. Alright? So, that's one part of it. The other part of it is, I got to now worry about the conjugate base affecting the whole deal. And it is. It was always there. It was always making an issue of things, but it didn't enter in the calculations because it was so small. Well, now I'm at the equivalence point and it becomes significant. So, since I no longer have any of the original acid, all of the H plus has been neutralized. The base now is going to act as a Bronsted-Lowry base. C2H3O2 minus is going to react with water. There's tons of water in there. And it's going to end up forming HC2H3O2 plus OH minus. That OH minus is going to have a dramatic effect on the pH, so I need to calculate that. Well, how in the heck do I calculate that? Well, I'm going to do, there's lots of ways sort of to do it, but I'm going to find the number of moles of this, because that's what I need. And then with the moles, I'll find the new volume. If I had 50 milliliters or 0.05 liters, of a 1 molar solution of acid in the first place. That means I have 0.05 moles of the acid. And I'll write that out of the C2H3O2. Or, yeah, of the HC2H3O2. That's how much I start out with. And because of this that I was talking about, how all of that now has been neutralized, left behind the same number, 0.05 moles of the C2H3O2 minus. Well, it's in a new volume, alright? So I got to figure out what the new volume is going to be. Well, the new volume is 100 milliliters. So I'm going to take that 0.05 moles of the salt, divide it by 0.1 liter, and what I'm going to end up with is 0.5 molar. Alright? So that is the concentration now of the acetate ion. And when I go to figure this out, I can plug that 0.5 molar, so I'll get rid of this, because you saw me do this, where that came from. Okay? So that means at this point, I have 0.5 molar of the salt, X of this, and X of that. So, good news for me is I need a mass action expression to figure this one out. Setting it up, it's going to be x squared over 0.5, which is the concentration right there of that, equaling. Now I got to use this is a base reaction because of the formation of the OH minus. So my Ka no longer works. I need to figure out what the Kb is for the conjugate base acting as a base. Well, it's easy to do because Kb for this reaction is going to be equal to Kw divided by the Ka that I used when it was acting, when the acetic acid was acting as an acid. So that means it's going to be 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. Alright, so now if I go through and solve that, if I take 0.5 times 1 to the negative 14th divided by 1.8 to the negative 5th, take the square root of that, I end up with x being equal to 1.67 times 10 to the negative 5th. Alright, now this 1.67 times 10 to the negative 5th, this x, or at least one of these x's, was a hydroxide ion. Alright, so that means the OH minus hydroxide ion is that 1.67 times 10 to the negative 5th. And if I go through and find the negative log of it, I'm going to end up with a POH. We'll do that. Take the negative log of 1.67 times 10 to the negative 5th, and you get a POH of 4.78, since pH plus POH equals 14, I subtract the 4.78 from 14, I end up with a final pH equal to 9.22. And that's characteristic of a weak acid because it's going to have a higher pH due to the salt, the anion, acting now as a Bronsted-Lowry base, pulling a hydrogen off water, leaving behind a hydroxide that's still in solution. So I just went through and calculated all of those